So good afternoon, and really a big thank you to you, our faithful audience, because without your regular attendance, your encouraging comments, your emails, your willingness to share the YouTube link with your own colleagues and friends, we would not be here where we are today. So really a big thank you. It's because you keep coming back that we keep presenting bite-sized corrosion. Now, today, as always, we hope to present another aspect of corrosion-related information that we hope you will find interesting, informative, and that you'll feel that you've not wasted this time with us, but really learned something to help you in your journey. Today is our final episode in our three-part bite-sized corrosion series, where we've been looking at corrosion protection of marine infrastructure. During the series, we've taken a second look at marine infrastructure and have considered some of the corrosion challenges in protecting very deep infrastructure, internal facets of hollow piles, and also some corrosion considerations with marine structures located closer to the shore. If you've missed any of our conversations, as always, please visit our YouTube channel and watch them. Today, I'm delighted to welcome Neil back to the microphone. As you're all aware, Neil has devoted his life to fighting corrosion, often using cathodic protection. He's always very willing to share his expertise with us, and I have no doubt we'll learn from him today. So welcome, Neil, and thank you for joining us. Neil, over the past couple of sessions, we've explored some of the challenges associated with protecting marine infrastructure from corroding, but I thought you might like to share some of your more challenging and maybe interesting marine corrosion experiences with us.
Well, yes, I'll start with what is now, looking back, a rather funny story, although it wasn't funny at the time. Last week, Sean was talking about dolphins, and you
Yes.
sort of jokingly mentioned that how do you protect dolphins? Well, that reminded me of a project that happened, which was related to sharks. And it happened at an aquarium where they had a seawater tank. And in this seawater tank, they had a ragged-toothed shark and a loggerhead turtle. And this tank obviously had seawater in it and 80 millimeter thick plexiglass observation panes set into steel frames. And these steel frames had started to corrode on the inside. So we thought, well, about the only thing you can do in that situation is apply an underwater epoxy, because you can't put any electrical system in there because of the danger to these marine inhabitants. And so we got hold of an underwater grade epoxy. This we first had to test for toxicity by coating a panel and putting it into a small aquarium with tilapia. So we put these into a tank with some tilapia to check whether the tilapia would die. Fortunately, they didn't die, which meant that the stuff was acceptable for use. So in spite of all their certifications, they said, no, you've got to make sure that it doesn't kill the tilapia. So anyway, it didn't kill the tilapia. So then now we're going to go in and attempt to apply this underwater epoxy to the steel frame where it was corroding. So yours truly dons his scuba gear, having only ever dived once before in my life, and jumps into a tank complete with a ragged-toothed shark and a loggerhead turtle. And I must say, it's one of the few occasions where my heart was in my mouth. And the aquarium keeper was very blasé about this. He says, don't worry about the shark, it's the turtle you've got to look out for. So they steered the turtle away whilst I was in the tank, and the shark just swam around near the surface, and I was down near the bottom. And I've got a lovely picture that somebody snapped of me through the plexiglass. Of this. So the first dive was to check the condition of the steel, and where the coating of the steel frame had failed, there was a gray corrosion product, which was rather unusual because corrosion products should be brown or rusty. And so we dug away this corrosion product, exposed the clean steel underneath, and there was quite significant corrosion. It was a couple of millimeters. And then went back to the surface, pre-mixed the squish pack of underwater epoxy, went back down underneath, and this stuff would not stick. It would not stick to the steel, full stop. It didn't matter what we did. It stuck to me. It stuck to my wetsuit. It stuck to the concrete. It stuck to the plexiglass, but it would not stick to the steel. Eventually, we gave up. And in conversation then with the operators, we discovered that they had put in a sodium molybdate inhibitor into the water. And this inhibitor had coated the steel in spite of the fact that there was this corrosion, and it was preventing the epoxy from sticking. It formed such an effective inhibited layer on the steel that it completely repelled this underwater epoxy, which is designed to stick to everything, and it did. As we discovered. So that was a very interesting experience, and it's one of the few projects where we've actually had to abandon the project and say, sorry, no can do.
Yeah, well, thank you for sharing that, Neil. And let's be grateful that that turtle didn't decide to take a chunk out of you. I was there at the time, and it was fascinating, but it was a little daunting with that. Yeah, as they rightly said, the shark was of far less concern than that jolly turtle. It was really keen to have you for breakfast. Anyway, let's move to the real ocean. When we had our discussion with Frances a couple of sessions ago, she was indicating that to some extent, sacrificial anode cathodic protection may be falling out of favor for offshore structures. And I wondered what your response to that would be. Obviously, she's using an impressed current system on their deep piles.
I think it's a challenging situation because the environmental watchdogs are saying that sacrificial anodes discharge heavy metals into the ocean, and that's a no-no. The heavy metals we're talking about, of course, are zinc as a sacrificial anode primarily, and historically, we also did have aluminium anodes which were inoculated with mercury and or cadmium, which are also no-nos. And those particular alloys have also been outlawed. They're no longer allowed to be used. And so there is certainly a move against the use of sacrificial anodes. Whether it's going to apply to all sacrificial anodes or not remains to be seen. It's primarily focused at zinc at the moment. But the challenge, of course, is that it's all very well to talk about putting an impressed current system on an offshore structure. But when your offshore structure needs 2,600 amps of protective current, it's a bit difficult. It's a bit difficult to apply that by impressed current. I mean, how on earth do you discharge 2,600 amps fed from cables? It's a logistical nightmare. In fact, it's really not even practical to do it. So some of the smaller structures, perhaps, if they are well coated, you might be able to then use impressed current systems where you have very small current requirements. But a medium-sized offshore platform, like, for example, the FA platform off South Africa, it's the only one we've got, but it's typical of any platform anywhere in the world. It's 100 meters or so deep, slightly over 100 meters deep. We're talking about 3,000 square meters of bare steel, plus a lesser quantity of coated steel, which is in areas of high density, like around the pile clusters and things like that. And you've got the piles themselves, which represent another few thousand square meters of steel in the marine sediments. Now, the marine sediments have a much lower current requirements, but you're still talking about milliamps per square meter as opposed to microamps per square meter, which is what we used to talking about for onshore pipelines.
For pipelines.
And cathodic protection where we use impressed current all the time. So you would, for impressed current systems to be viable offshore, you would have to get coating systems that are equivalent to the polyethylenes and things like that we use onshore. And to try and do that in an offshore structure is pretty much impossible. It's not impossible, but at the end of the day, financially, totally impractical. So on bare offshore structures, which is the norm, sacrificial anodes are the only way.
Right.
And you can refine it by coating certain areas, as I mentioned, like the pile clusters, to reduce the quantity of material required and to improve the distribution of current. And the rest is bare. And we rely on the current to form a calcareous deposit on the surface under the high pH conditions that you get with cathodic protection. And then that acts as a coating which reduces the current, but you're still talking about an average current over the lifetime of the structure of 70 milliamps a square meter. So take 30,000 square meters of bare steel at 70 milliamps,
Yeah,
that's
that's a
2,100 amps.
So Neil, just thinking about that, those numbers are a little bit mind-boggling. And the question I have is that to get that current, you need a lot of weight of your anode. And
Yeah.
surely that must also provide a challenge in terms of the design, in terms of the fact that they're consumed and need to be replaced. How do you even work with that kind of challenge?
It's certainly an interesting aspect because in the design of an offshore platform or jacket, one of the primary centers of focus is weight control.
Mhm.
How thick are your structures? How heavy is the equipment that you're going to put up on the top? And when you add 400 tons of metal in the form of sacrificial anodes, it's a significant addition to the weight of the
Of the
structure,
overall
and of
structure.
course then to its strength, because these anodes stick out from
Mm,
the structure and provide increased drag from ocean currents. So it means your structural strength is affected as well. And the design then is based on how long do you want the structure to last.
mm,
So, the oldest structures are dating back to what, 19,
70s.
maybe late 60s, early
Mm,
70s. So they're
mm,
all 50 years old now. And I remember when we designed the FA platform, the design life was 30 years that we had to design for. And the codes that we used at the time were the 1986 codes. And so the design was done based on those codes. And then a few couple of years back in 2022, they wanted to look at life extension.
wow.
And by this time now, we've already, in theory, got to the end of life
Yeah.
of the jacket. And yet, the anodes are still there and they're still working. And the whole thing is still functional. And when you looked at the 2021 codes, still the same DNV code, the projections that were done in the 80s have been refined based on
Mhm.
practical experience. And so we actually still had significant life left. There was a presentation at iCore a few months back of a project where they had mapped the performance of a CP system on a jacket that was done in the late 70s. And this system was fully protected for 35 years with no measurable change in the cathodic protection levels. And then they started to see a decrease in protection level, which was then plotted over a number of years. And
Mhm.
I think it only, I might be wrong, and I'm welcome anybody to comment on that. But if I remember correctly, by the time it got to 45 years, the structure was no longer fully protected in terms
Okay.
of the minus 800 criterion to silver chloride.
Yes.
What they did then was to design and install supplementary anodes on tensioned sausage strings, which were installed between the bottom frame of the jacket and the top frame of the jacket.
Okay.
And that was how they then extended the life of that particular jacket.
That's interesting because I was just going to say to you, so if the anodes have reached the end of life, retrofitting anodes isn't as easy as digging another hole in the ground next to the pipe and throwing in an
Uh-uh.
anode.
Yeah.
And even measuring life, I imagine, is quite challenging because you're going to have to be using divers where you can and ROVs
Yeah.
because a
So
lot of
that
these are
that
so deep.
that's exactly what they do. So the anode dimensions are known to
Mm,
start with, and the divers go down with potential measuring devices, and they can measure the polarized potential of the jacket at in those do a survey of the entire
mm,
structure, and you can measure the potential, and then they physically measure the anodes to see how
Right.
much anode is left. And they do
Right.
that by measuring the circumference, which generally
Yes.
the anodes would have started out either as cylindrical or trapezoidal. So
Mm.
you can, by measuring it, you can determine how much of the anode has actually been consumed or how much is left. And provided you do that on a regular basis, you can plot the life of the anode and the operating life of the structure. And so it is a wonderful example of the necessity to do regular routine maintenance or monitoring. Because if you don't have that, you cannot predict where you're going to. You can't go from 22 years ago, use a single point
Mm.
and project it to 45 years
Yes.
because the degradation rate is not linear.
Yeah. And I'm sure as we get more examples from the field of this, I mean, you mentioned the one presented at the conference, at the ICOR conference, but as we get more of that data becoming accessible, we will also find ourselves understanding the systems a little bit more. And then I'm sure there'll be modeling packages developed that can accurately predict. But there are a lot of unknowns. We just don't know how quickly that drop off will be. And of course, you can't afford to leave the steel unprotected because then you may as well not bother with the structure at all.
Right. Yeah, no, then you let it corrode and fall to the floor, except you're not allowed to do that. I don't know.
Well,
It's an interesting point. I don't know what they actually do with dead jackets
I don't know.
or dead platforms. Yeah.
Yeah, maybe
Like, I
people.
mean, not the bit more difficult than a dead ship. I mean, a dead ship, you send it off to a breaker's yard and they chop it up and they recycle it. But an offshore platform is pinned into the ground
Yeah,
very solidly.
one would
Yeah.
hope so. Otherwise, there would be more environmental disasters, and I'm glad there aren't. Neil, just looking back over your long career, have there been some standout offshore designs that you've been involved in that have piqued your interest because of either their physical location in the world or their complexity in terms of the design?
You know, the design basics for offshore are quite intricate compared to onshore because you have this challenge of designing against an initial situation where the structure is first installed, and you're putting this into a very, very aggressive environment where the coatings are subjected to both seawater from a chemical point of view, if you want to call it that, and the physical point of view.
Mhm.
They have to be able to resist the effects of marine fouling. And I don't mean, chickens flying around, but
Yes.
barnacles growing and things like that. I think one of the things that stands out for me, an example that stands out is not a success story, but it was a situation where a barge came into dry dock for
Mhm.
refit, and the barge was fitted with impressed current. Now, that is a marine situation where impressed current really does work, is on
Mhm.
ships
Okay.
because you have power on the ship, obviously.
Mm.
You can fit relatively few anodes, and the ships get recoated on a regular basis.
Frequently,
They dry
yes.
dock every two
5
years or
years or
5 years or whatever it is. And anyway, this thing had come in for refitting, and it was fitted with impressed current anodes. And the vessel was scheduled to go out the following week. Came to the final recoating of the external of the hull, and the contractor managed to destroy the impressed current anodes. They didn't mask them,
I was
and
going to
they
say they
just
coated them.
blasted. They blasted them.
I blasted them.
And
Oh, good
these
grief.
were platinized niobium anodes.
Ooh.
So a platinized niobium anode is an interesting beast because it's a rod of niobium with a platinum wire swaged in a spiral over the niobium, made by Lockheed in the United States. And this vessel now is sailing in 10 days' time. And the chances of getting new anodes from
It's about
Lockheed
zero.
in 10 days is about zero. We managed to get a local company, to manufacture MMO-coated titanium anodes of the same dimensions and same rating, and air freighted them, air couriered them from Durban to Cape Town, and got them fitted 24 hours before the vessel sailed. It was
that's a nail biting
that was a
experience.
nail biting experience. Yeah, yeah.
But the CP system worked, and that at the end of the day, another asset was kept going, which is great.
Yes.
Well, Neil,
Yeah.
thank you. Thank you for yet another interesting discussion. Thank you for sharing some of your background, your experience with cathodic protection, some of the real challenges that need to be taken into account. And I'm certain that our audience will join me in saying thank you for a stimulating and interesting discussion.